Hello, Tigers. Today we are going to be working with division properties of exponents. I can determine the properties of integer exponents, including quotient of powers. So we know that a quotient is the answer to a division problem. Note, when dividing powers with the same base for every non-zero number, a and integers m and n, we have a raised to the m power divided by a to the n, and this tells us that all we're really going to do is to subtract the exponents. Another reminder, we've talked about this each lesson, is that anytime you have a base raised to a negative exponent, it is not okay to end up with a negative exponent, so we turn that into a fraction, 1 over a raised to the nth power. So copy and complete each equation. We have 5 raised to the 6th power over 5 raised to the 2nd power. So according to what we just read, if we had 5 raised to the 6th power, and we do have the same base, so we're talking about 5 and 5, then we're going to take the numerator exponent and just subtract the denominator exponent. So we end up then with 5 raised to the 4th power. Now, why does that work? Let me go ahead and write this out for you. If I had 5 raised to the 6th power, it looks like this. 5 and 6, nice 5, all over 5 raised to the 2nd power. So if I'm multiplying by 5s on the numerator and then turning around and dividing by 5s in the denominator, then that means that this 5 would cancel with a 5. This one is also going to cancel with a 5 because we know that 5 and 5 share a factor of 5. So then all that would be left here is 5 raised to the 4th power. You don't have to show all of that. You don't have to show the work on that. All you have to do is show, just like we've been doing with multiplication, you just show what did you subtract in order to get 5 raised to the 4th power. Also, another reminder is we are dividing, but still make sure that you are subtracting the exponents. On number 2, I have 3 raised to the 2nd power all over 3 raised to the 5th power. So if I'm following the rules, the base is the same. So the base is a 3. So we have 3, and then we take the numerator exponent and we subtract the denominator exponent. I end up with 3 raised to the negative 3rd power. Now on this exercise, all we're doing is just kind of getting warmed up and practicing how would I get the new exponent. But we know that if I was supposed to simplify, then I cannot have a negative exponent. So if you got to the step and you were trying to simplify, then you would have to go one step farther. The base is 3. We have 1 as the numerator, the 3 goes to the denominator, and the negative 3 would become a positive 3 here. So your final answer would be 1 raised or over 3 raised to the 3rd power, or 1 over 3 times 3 times 3, which is 27. So again, in this exercise, all we're doing is filling in the box. But if I was to simplify, I just want to remind you to never leave a negative exponent. It has to be changed into the positive. You're going to see that on the next example. Simplify each expression. So we have b raised to the 4th all over b raised to the 9th power. The base is the same. It's a b. So we're going to take the numerator exponent and subtract the denominator exponent. So we end up with b raised to the negative 5th power. We have a problem. We have a negative exponent. So if we have a negative exponent, I change that into 1 numerator. B goes to the denominator, and the negative 5 becomes a positive 5. There, my friends, is your final answer. I would like you to pause the video and go ahead and try to do number 2 on your own. And when you are finished, then start up the video. Number 2, z raised to the 10th power. So I have z 10. That's the numerator exponent. And I'm going to subtract the denominator exponent. So that's simply z to the 7th. Before I circle my answer and I'm ready to move on to the next example, I want to remind myself, that if this is a negative, then I would need to change that into 1 over z to the 7th, but it's not. It's positive. So we are done with that problem. We have z raised to the 7th power. Number 3. So now I see a fraction. I see a couple different things going on with this problem. I see an m, I see n's, I see that they are raised to um, powers of their own within the numerator and the denominator. So the easiest way to do this is to separate it out. I've got an m, I have an m. So looking at the exponent of m, I've got m raised to the negative first, and then I'm going to subtract the denominator exponent, looking first at the m's, that's all we're concentrating on now, and then do the same thing with the n. So n, and I have my numerator exponent too, and then my denominator exponent, I don't see it, but it's there, so it's really important for you to write this in so that you know that when you subtract, there is actually something. If you're thinking of that as n to the 0, then you would miss it. So we want to make sure we remember that it's n raised to the first power. So then I have m, and then negative 1 minus 3 would be a negative 4. And then times n, 2 minus 1 gives me n to the first. It's not necessary to write the first, but that is correct, mathematically correct. So, ooh, I see a negative exponent. So I know that my final answer, it does say right up front to simplify, I can't have a negative exponent. So we're going to write m as 1 over m raised to the 4th times n on the top. Well, when I simplify, if I multiply across, if it helps, you can put n over 1 so that we remember we multiply numerators, we multiply denominators. So 1 times n is n, and then m to the 4th times 1 is just m to the 4th. And that's it. Don't try it. You can't simplify from there. N and m are two different variables. So just to recap, what did we do on this problem? We found the base. The common base was m and m here. So I subtracted the denominator 3 from the numerator exponent, negative 1, and I ended up with a negative 4. The n's was n raised to the 2nd minus 1. M raised to the negative 4th, we know we can't have a negative exponent, so we rewrote it using a fraction. So negative 4 becomes positive in the denominator, n to the first is just n, and then I can multiply across. So 1 times n is n, m raised to the 4th times 1 is m to the 4th. And there's our final answer. Simplify each expression. When I have a fraction raised to a power, it's just like distributing. So that's the first thing I want to do is just rewrite this with the exponent on both. So that would be 3 raised to the 2nd all over x to the 2nd raised to the 2nd power. And you learned that in your last lesson that when I have a power raised to a power, then I multiply the exponents together. So what does that end up looking like? Well, 3 raised to the 2nd is 9. That means 3 times 3. And then that's going to be over x raised to the 4th power. So remember that when you have a power to a power, that 2 times 2 was a multiplication, not an addition, because that can be confusing because 2 plus 2 is 4 and 2 times 2 is 4, and that is your final answer. Remember that it's perfectly acceptable to have a fraction, you just can't have a negative exponent. Looking at number 2, I've got x raised to the 3rd power. So that's the first thing I'm going to do is just rewrite that so that I can see the exponent right there next to the variable. And then I've got y raised to the 2nd. Well, if it's a power to a power, then that means y raised to the 2 times 3. Please show that step. Final answer, x to the 3rd over y raised to the 6th power. Let's look at number 3. So now the difference between the second example and the third example is that I have really, if you're looking for a coefficient, if this is a 1 in front of it, we know that anytime there isn't a number in front of a variable, then it is a coefficient of 1. So if we played this out and said 1x, then the 3 would apply to the 1 and the 3 would apply to the x. But the thing is that 1 raised to the third power we know is still 1, so there's really no reason it's unnecessary to show raising those numbers to a power. But then came number 3. The first thing that I would do on number 3 is actually simplify, because I see a 3 and I see 15, and I know that I can take 3 into 15. So if that's the case, then 3 over 15 would be x to the fifth, and then I'm going to raise that to the second power. So now that coefficient of 3 really just went away and it became a 1. So raising x over 5, to the second power means x over 2, and then on the denominator we'd have 5 raised to the second. That ends up being x squared over 25. Now let's say that you forgot and you raised, let's say you weren't thinking in terms of simplifying, then you could So let's say that we forgot to simplify 3 to the 15th. Let's just see how that's going to play out doing this problem a different way. So instead, I would apply the 3 to the 2. So I'd have 3 raised to the second times x raised to the second, because we talk about the distributive property being very generous. It wants to be a part of everything that's going on. And then that would be all over 15 raised to the second power. All right, well then our numbers become a lot larger, but we're still going to get there. So when I multiply, I've got 3 to the second, and that's going to be 9x squared all over 225. Well, 9 goes into 225, guess what? 25 times, so we end up with x squared all over 25. So no matter what, we're still going to get x to the second over 25. So you mean that if I look at the fraction and I recognize up front that I can simplify, then I'm going to be dealing with smaller numbers. Yep, that would be my advice to you, is to try to recognize that before you apply the exponent. Now, on this last example, we have a power raised to a power. So there's a couple different things going on here. We have our fraction, which means it's a quotient, but then we also have a power to a power. So this problem is going to be a lot easier if I recognize that this is a -4. Anytime you have a negative exponent, all you really have to do is to flip-flop the numerator and the denominator. So in other words, you're going to flip-flop the numerator and the denominator. So now you have n raised to the -2nd over n raised to the 4th, and then now it's a positive exponent. So take a deep breath. You mean a power to a power, it's a negative exponent. I flip-flop the numerator and the denominator, and then I raise it to the positive 4th. That is exactly right. If you do that, there is another way to do it, but then you're going to end up with some fractions and it's going to be a lot more challenging. Just try to remember to raise it to the 4th power. And in other words, raise it to the 4th, but to flip-flop the numerator and denominator. Now, what do I do from here? So I've got n raised to the -2 times 4th power, because the power to a power we know to multiply. And then I have n raised to the 4th times 4. I end up with n raised to the -8th all over n raised to the 16th. I'm dividing. I have it to simplify. So what do I do? Oh yeah, today our focus is quotients, so that means n raised to the -8th minus 16. Remember, we talk about numerator exponent minus denominator exponent, so I end up with n raised to the -24th power. And once again, we have a problem, because before I circle my answer, I remember right away that I can't have a negative exponent. The negative exponent has to become a positive exponent. So the positive exponent, n raised to the -24th, I write that as 1 over n to the 24th, and then I'm golden. That is going to do it for us for division properties of exponents.